This should be x minus 4 to the 10th. And then this should be x plus 3 to the 4th. And then this one should be 4, 6. So 4x minus 1 to the 6th. And then this one should be x plus 2 to the 12th, right? Okay. That's it. That's the derivative. It is all the stuff we did, right? And then we had to multiply both sides by y. So here's y. I still think that's better than what it would have taken had we not done the logarithmic differentiation. We should see another one of these. But something completely different, something that doesn't look like this one. Think back. If this is like your first time in Calculus 1, you know, think back to the beginning of this. Do you remember when I was like, the derivative of x to the n is equal to n x to the n minus 1? I gave us this rule, and I was like, wow, this is going to be such a powerful rule. I mean, think about now how we've expanded what we can take the derivative of, right? Using all these rules together, we really have opened up what it is possible to differentiate. We've come a long way, is what I'm saying. Okay, let's see here. Oh yeah. Yeah, these are fun. How about this one? Let's graph this one first before. I want to make sure that I've always wanted to know what the graph of cosine of x raised to the cosine of x looked like.
Whoa. It's like the mustaches. Oh my God.
Cosine of x raised to the cosine of x.
It's Pikachu's mouth.
I'm curious. So we do have graph, don't we? We do have graph, which means we should have derivatives somewhere. So what is cosine of x raised to the cosine of x? What is its derivative? And so look, in this problem, we have run into something we have never seen before, ever. Probably in all of your life in math, you have never seen this type of function. And what I mean by that is you've never had your variable appear in both the base and the exponent. Like you've seen this, you've seen like x to the 4th, and you've seen 4 to the x. This is called a power function, and this is called an exponential function. You've even seen slightly more complicated problems like sine to the 4th x, right? But see, your variable is in the base, your exponent is a number. Or maybe this one you could say 4 to the sine x. Here, your variable is in the exponent, but your base is a number. You've never had your base include your variable and your exponent include your variable ever. Right? Is that safe to say you've never seen that before? So how do you take the derivative of something like that? Because it's not this, right? It's not x is in the bottom and you have a constant or a constant up to here, a power. And it's not this because your base is not a constant. So it's neither one of these, right? It doesn't fall into either one of these categories. Is that clear? So let's try logarithmic differentiation. So I'm going to take the natural log, apply it to both sides. Like that. And what can I do on the right-hand side? Move what to the front? The cosine x. See, I have natural log of something to a power, right? So that power can come down. And so this becomes natural log of y equals cosine x times natural log of cosine x. Right? That is such a powerful property. This is such a powerful property in college algebra. We use it so much in calculus that you can always take this power and drop it out front. And that power does not have to be a number. It can be an actual function of x also. Like it can involve the variable x. All right. At this point, we should be pretty comfortable taking the derivative. Do y'all realize why I had to do this? Because if I try and differentiate this, I can't. I cannot differentiate this as it is because I don't know what the derivative of cosine to the cosine x is. If I did, I would have done it to begin with. But by pulling the cosine out, now I've created a product that I can take the derivative of. Yeah? Okay, so implicit differentiation. Derivative of the left side. 1 over y prime. That's always going to be the case. Okay, that's the good news. On the implicit differentiation, your left side is always going to be 1 over y prime. The right side, however, is a product. So what is the derivative of that product? Negative sine x times ln of cosine x plus 1 over cosine x times negative sine x times cosine x. So when I took derivative of cosine, I got negative sine, then times this, plus derivative of this is 1 over what's inside, times the derivative of what's inside, times this. 1 over y prime, or 1 over y prime is negative sine x, natural log cosine x, minus tangent x, cosine x. I just decided to write the sine over cosine. Oh, wait, no, hold on. Let's cancel the cosines. Yeah, let's cancel those cosines. That's better. How about just minus sine x? We're not done. Multiply both sides by y, right? So multiply this side by y, you just get y prime. If you multiply this side by y, you just take this side, throw it in a big parenthesis, and you multiply it times y. And y was the original function, right? This is what y is. So it's cosine x to the cosine x.
You can factor out a sine x, right?
You could have factored a sine x out of here. Yes, a negative sine x, in fact. I'm just curious. This graph, did it have a point? Was there a point 0 something on this graph? What's cosine of 0? 1. So this is 1 raised to the 1, which is 1, isn't it? So that point lives on the graph, doesn't it? 0, 1. What is the slope of the tangent line there? So we could come over here, right? Plug in 0, and we would get 0 here, and this would be natural log of 1, which is 0, and this would turn out to be 0. So we should have a flat tangent line there at 0, 1. And I think we did. Yeah, there it was. Here's 0, 1, that little top of the mustache right there. The slope of the tangent line there is 0. I'm just showing you like it matches up. Like our answer is somewhat confirmed with the picture. All right. Y'all like that? Logarithmic differentiation. You know, that property that I was talking about that I'm saying was so important, you know? I'll never forget when I first started working here, I was in an office My office used to be out in the portable buildings. Those portable buildings that are over there by the parking garage.
They used to be like main campus.
I liked being out there. It was awesome. Anyways, I had a colleague of mine, and we were both in graduate school at the same period of time. We didn't have class together, but anyway, this guy, I didn't like him. You'd have to know him to understand. But we used to give each other like challenge problems and stuff to see if we could figure out. Now, remember he gave me this problem. It was x to the x to the x to the x forever equals 2, and to solve for x. So what is x so that when you raise it to itself infinitely many times, you get the number 2? All right? So this can be done pretty easily if you use this property that I just showed you. This right here. Okay? So here's how we can do it. We can say that the log of x to the x to the x to the x is equal to the log of 2, right? And then I can treat everything from here up as the power. All right?
Like everything?
Like, no, not this x, but this and on.
Yeah, all of it.
All of it, forever, okay? As the power, and I can pop that out front. Okay, so now I have x to the x to the x forever. Natural log of x equals natural log of 2, right? But what is x to the x to the x to the x forever supposed to be equal to? If I'm going to solve this equation, what is x to the x forever supposed to be?
2.
It's supposed to be 2, right? So I'm going to replace this with 2. See, by taking out 1x off the bottom of this, the fact that I have infinitely many does not impact the fact that this should still be 2. It's weird, but stick with me here. So this is 2. Natural log of x equals natural log of 2, right? And then what I'll do is I'll divide both sides by 2. So this becomes natural log of x equals 1/2 natural log 2, right? And then what I'll do is I'll reverse the property and I'll pop the 1/2 up here. Natural log of x equals natural log of 2 to the half. And what's 2 to the half? Root 2. So natural log of x equals natural log of root 2. And now if I do e on both sides, the e and the natural log kill each other off, and you get x is equal to root 2. So that's the answer. If you take the root 2 to the root 2 to the root 2 to the root 2 forever, that's 2. It's weird. But I can remember, that's why I've always loved this property, because you can use it in places that you wouldn't even think you could use it.
Does that work for any root?
Are you saying if this was a 3?
Yeah.
That's a great question. If that was a 3, are you saying is the answer root 3?
Yeah.
Do you think it is?
I don't think so, no.
It's close, but it's not root 3. It's... Think about what we did here. Let's just replace this. 3, 3, 3,
So it'd be cube root?
3,
Oh, it's the cube root.
3, 3, 3, 3, cube root 3. It's cube root 3. And then what would this be? 4th root of 4. So in general,
So it's n root n.
is the nth root of n. See, that mathematicians want to generalize, okay? Show one example, great, but can we generalize it? Can we actually come up with a formula for this? Solve for x. That's x. So long as n is a positive, n has to be a positive number here, this doesn't work at all. But all right, way off on a tangent there, sorry.
Sir, how long did it take you to figure it out?
I saw it right away.
Was it mad?
I don't remember if he was mad.
I heard he solved the same way.
I don't know if he had the answer, actually. I don't know if he did. I think he was just trying to give me a hard problem he couldn't figure out. Look, this guy was really, I didn't like him, okay?
You were on his Christmas mailer?
He wound up losing his job for Not here, he was a different place, but he did some stuff you're not supposed to do. Anyway, okay. We're going to change into the next section, all right? We're gonna move. You need to do your homework for 3-3. I mean, that's, at this point, I've kind of shown you some demonstration, but now you've got to go in there and get your hands dirty. You've got my video solutions. Use them the right way, and you should hopefully be able to get your head around this. All right, so now the next two sections, actually, I'm not going to do this. That 3-6 you will do in Cal 2. And a lot of Cal 2 classes do 3-5 also. So I'm just going to show you 3-5. That's it. Just going to show it to you. It's very short. We will not go into detail about the inverse trig functions. We will just state the formulas for their derivatives. So remember from pre-calculus that you had these inverse trig functions. Do you all remember that? You had the sine function, but then we defined its inverse. And then we had the cosine function, we defined its inverse. Tangent, cosecant, all of them. Well, if we wanted to know what their derivatives were, here's what they are. All right? You do not need to memorize these at this point. Just know that they're out there and they're on your formula sheets. All right? The most important one out of all of these is this one right here. This one comes up a lot in Cal 2. The derivative of the arctangent function is 1 over 1 plus x squared. That you will see a lot.
I was about to ask why we teach in Cal 2, but now I'm kind of understanding why.
Why they wait?
Yeah.
Yeah. I mean, you can do it. You know what? I'll do it for just this one, all right? Why don't we just, because this one's so important, let's try and figure out why that is what it is, all right? I'll just show you for this one. Okay, so I'm going to try and prove to you that the derivative of the inverse tangent function is 1 over 1 plus x squared, all right? Here's what I'm going to do to do that. I'm going to start out by writing out y equals the arctangent function, okay? Right now I cannot take the derivative. I cannot take the derivative of the left and the right because I don't know the derivative of the right side, right? I don't. So what I'm going to do instead is I'm going to try and manipulate this into something that I do know the derivative of. So how about this? How about I take tangent of both sides? Well, tangent of y, tangent of arctangent of x. What should the right side turn out to be? Just x, right? Because that's what happens when you put a function together with its inverse. They wipe each other out and you just get the x to pop out. So here's what I have. Now I'm trying to figure out what the derivative of this is, right? I'm trying to figure out what y prime is. I couldn't, so I did this, and now I'm here. Now I'm going to take the derivative implicitly with respect to x. See, because I know the derivative of tangent and I know the derivative of x. What is the derivative of tangent of y? Be careful. Secant squared y times dy dx, which is y prime. That okay? Equals the right side. What's the derivative of the right side? 1. All right, I've got y prime there, don't I? Y'all following me? Okay, so y prime equals 1 over secant squared y. Do you agree? Well, that doesn't really help. Y prime equals 1 over secant is really cosine, isn't it? So isn't this cosine squared y? So I've found what y prime is. The problem is y prime has y in it, not x. And I'm supposed to show you that it's equal to this, right? So now what I'm going to do is I'm going to go back and I'm going to use something that you used in pre-cal. I know if you had me for pre-cal, I told you how important this idea of a reference triangle is. So I want you to look at what I boxed there. I'm going to draw a triangle. A right triangle. And I'm going to label this as the angle that I'm talking about there. What is the angle in that equation? The angle is y, right? So if I put y here, then if I want this triangle to match this equation, this should be tangent is opposite over adjacent, isn't it? So if I label this as x and I label this as 1, then x over 1 is x, right? So this triangle matches that equation. Agreed? We call this a reference triangle. Okay. What is the answer? It's cosine of y squared. Oh, well, what's cosine of y on this triangle? Cosine is which side over which side? Adjacent over hypotenuse. I don't know the hypotenuse, or do I? Pythagorean identity. A squared plus b squared is c squared, right? So this side should be 1 plus x squared, right? But what? Square root. If I give you two sides of a right triangle, we can always solve for the third side, or the hypotenuse here, right? So take a look at this formula here. This is cosine of y squared. What's cosine of y? Adjacent over hypotenuse. But all of that squared. And when you square that, what do you get? You get that. Okay, so that I'm not going to go and do any more of these, but you get the idea, kind of? All right. You can actually derive the formulas for all of those. And in Cal 2, I derive, some of these are a little more complicated, but they all work out the same way. You take whatever the trig function is here, whatever inverse trig function you have, you take the actual trig function of it. So if this was secant inverse, you would do secant on both sides. You'd have an equation, you'd go implicit differentiation, you'd solve for y prime, you would draw a reference triangle, figure out your sides, and come back and plug in. That's the way all of them are done. But just know that these derivatives exist, all right? In 3.6, we deal with the hyperbolic trig functions, which again, you've never even seen a hyperbolic trig function? You have not seen a sign with a little h in here, right? Not in any class. So in Cal 2 you will. We talk about those. These functions are actually pretty useful. I may talk about it. Where is it? I don't have it here. No, I don't have it in here. Yeah, because in Cal 2 we talk about the hyperbolic trig functions. Then we say, hey, each of those hyperbolic trig functions has an inverse, and then they all have derivatives, and yeah. But I've got about 20 minutes, so I can introduce you to your new friend L'Hopital. So because of L'Hopital, you really don't even do limits the old way, like, right? Is that what you're saying?
Not really, no.
Yeah. So Diego has a little experience with this, and he can vouch for the fact that this is important. Yeah. Useful? Yes. All right. Let's go back to one of the first things I ever showed you in terms of limits, where I was not able to prove what the answer was. And I told you to take it on faith. It was this one. You know, I think I used x. Let's use x. Do y'all remember what that limit was? I had told you to memorize it. What is this limit equal to? 1. And I didn't tell you why it's 1. I told you just had to know it, right? And the problem was that when we let x go to 0, we get 0 over 0. But there's no algebra or trick that we could do that allowed us to do this, right? In last class, I was trying to prove to you, remember last class I was trying to prove to you that the derivative of e to the x was itself? And I had worked it out, and I had gotten to a point where, if you look in your notes from last class, we were at this point right here. And I said that this right here goes to 1, and I said I can't show you why that's true, but it does, right? So today with L'Hopital, I'm going to show you why this is true and why this is true. All right? Here we had 0 over 0, and we couldn't figure out any algebra. So what is L'Hopital's rule? L'Hopital's rule says this. It's in the notes, but I like to write it down, just out of appreciation. L'Hopital's rule says this. If you have a limit, and it does not matter what the limit is, okay? It can be x going to 0, it can be x going to infinity, it can be h going to 0. It does not matter what this is, okay? And you have some function in a numerator over some other function in a denominator. Right? So you have a ratio of two things. If this limit is approaching 0 over 0 or positive or negative infinity over positive or negative infinity. I want to underline something here. If you take a limit and you ever see 0 over 0 or infinity over infinity, then here's the result of the rule. Then, if the limit exists, it is equal to the limit as whatever goes to whatever of f prime of x over g prime of x. That is L'Hopital's rule. So let's make sure we understand this. Starting from right now today, if you ever take a limit and you get 0 over 0 or infinity over infinity, it doesn't matter if it's positive, negative, anything here, as long as it's infinite over infinite. And weren't those always the two cases that caused us the worst grief? Yes. Right? This always caused us like algebra or some trick. This always caused us some algebra or some trick. So these are like the worst cases. If we ever see these, then if there is an answer to this limit, if the limit actually exists, then it's equal to the limit of the ratio of the derivatives of the functions. Not quotient rule. Do you all see that? This is not quotient rule. This is just saying, hey, look, if you ever see this crap, take the derivative of the top and the bottom separately and try and run the limit again and see what you get. All right? So that's the rule. It's so simple, but it's so powerful. Let's see. Let's go do the one with the sign first. Okay, so let's take as an example the limit as x goes to 0 of sine x over x. So we run our limit right now, right? And we get the form 0 over 0. In the past, we've said algebra or some trick. Now we say L'Hopital. All right? So what I'm going to do now is I'm going to apply L'Hopital's rule. So I'm going to say that this limit is equal to, now we need to somehow tell whoever's looking at our work that we're about to use L'Hopital's rule. Most books will put an H on top of the equal sign to let people know that they're using L'Hopital's rule. Sometimes they circle it. I don't know how, but for me, I don't know when this happened. I think I screwed up, and it's just always been a screw up. I use L for L'Hopital, okay? They use H because I don't know. I don't care what you use, but use something to let me know and let you know that you're applying this rule, all right? I'm going to do L because I've been doing L my whole life since I've learned it, all right? Okay, according to L'Hopital's rule, this limit, if it exists, should be equal to the limit as x goes to 0 of the derivative of the top. What's the derivative of the top? Cosine x over the derivative of the bottom. 1. See, no quotient rule. And now what we do is we look at this limit and we say, does this limit exist? So let x go to 0. What's cosine of 0? 1. The bottom doesn't even have x in it. So it's 1 over 1. It's 1. We're done. We're done. It's beautiful, isn't it? Let's do that other one with the e. Look at this one. Limit h goes to 0. We had e to the x times e to the h minus 1 over h, right? That's what we had. And I said that this goes to 1, and I said, but I can't show you how. Now I can show you. Also keep in mind, e to the x does not have h in it. Right? So this is not, it's almost like we're going to ignore that and just look at this. When we plugged h in, we got 0 over 0, didn't we?
Yes.
Okay, so this right here has the form of e to the x times 0 over 0. That's what it's looking like to us, right? So I am allowed to use L'Hopital's rule. Limit h goes to 0 of e to the x times what? What is the derivative of the top? What is the derivative of e to the h? E to the h. What is the derivative of minus 1? 0. So it's just e to the h on top, right? Over what's derivative of the bottom? 1. Now let h go to 0. You're going to have e to the x here times e to the 0 is 1. 1 over 1 is 1. So you get e to the x. Check.
L'Hopital's rule, did they just kind of twiddle their thumbs at like e to the x and like other types?
Before L'Hopital's rule, they just had to have a lot better algebra or trickier things to use. I mean, there are ways you can get to some of these without L'Hopital. It's just, it's like when we were using like hidden zeros to prove like the product rule or quotient. I mean, it's that type of stuff that is required. It's very high level algebra is required to get these limits to work. All right. Are you impressed or no? Let's look at another one. And then we're going to have a philosophical discussion about why we held this from you for so long. How about this one? Limit as x goes to infinity of x to the third plus x plus 1 over 5x cubed minus 4x minus 5. Okay, what happens with this limit if I let x go to infinity? X go to infinity. So here it's becoming infinite. So this becomes infinity plus 1. So the top is going to infinity. The bottom, infinity minus infinity. But remember we said the x cubed dominates the x. So this will go to infinity. Does anyone remember what I did when I saw this in the past? You look at like the highest power of x down here, and you have to come in with like 1 over something in the front. Remember that? Yeah. That's in the past now. Okay, so now I have infinity over infinity, right? Because of that, I'm going to use L'Hopital's rule, and I'm going to take the derivative of the top and bottom separately. What is the derivative of the top? 3x squared plus 1. What's the derivative of the bottom? 15x squared minus 4. Right? Oh man. Did that help? If I take that limit, what do I get? Infinity over infinity again, right? So just do it again. Do L'Hopital a second time. Now, you have to have infinity over infinity to do this, though. You can't just keep on doing L'Hopital forever. I mean, like, you have, each time you do it, you have to have 0 over 0 or infinity over infinity to do it. So I do have that still. And so the derivative of the top, 6x, derivative of the bottom, 30x. These x's cancel, and you just get 6 over 30, which is 1/5. 1/5. One more. You ready? How about this one? I know that a lot of you did not like this type of problem. And you were like desperately looking for a shortcut when I gave you these. You were like, I've got to be able to find some pattern or something. Do you remember this? What form do you get here when you do this? Tangent of 0 is 0, sine of 0. So you get 0 over 0. So do you remember what I did with these?
You like split them.
I like split it all apart, and then we had to say it would be really nice if we had like a 2x up here, but we can't just put a 2x here, we have to put it here, and then we slid things around. Remember all that magic that we were doing? That was one of the first times I did something like that, and you were, like, everyone was like, what? Yes? Okay. L'Hopital now. L'Hopital. What is the derivative of the top? Be careful. Secant squared of 5x times 5. Times 5. Don't forget you got chain rule there, right? Okay, over derivative of the bottom. Cosine of 2x times 2. Now just as a reminder, secant of 5x is the same as 1 over cosine of 5x, isn't it? That's what that is? Okay, so now let's try and plug in 0. Secant of 0 is 1 over cosine of 0. Cosine of 0 is 1, right? So when I plug 0 into this, I get 1 squared. 1 squared is 1. Here, plug in 0, I get 1 again, right? Times 2. So when I take my limit now, I don't get 0 over 0. I get 5 over 2. And we're done. All right. We're about to go, but now the philosophical question. And Diego, you're not allowed to answer. I know you know what I'm going to say. That's why I don't want you to answer. Well, maybe you can ask the question then.
No, I don't know.
Oh, you don't know? I thought you said you know. Okay. So philosophically here, and I want you to think about this because there is an answer to this. Why torture you in the beginning with all of this stuff? Right? Why not give you L'Hopital's rule earlier?
Because we didn't know the derivative.
That's exactly right. I would have been happy to give you L'Hopital's rule right off the bat. The problem is you don't know how to take a derivative. Right? So if I were to have walked in here and said, hey, you've got sine x over x. Just take the derivative. Cosine over 1, you would have been like, how does sine become cosine? You don't even know what a derivative is yet, right? So the idea is this. You have limits, right? In the very beginning of this course, we talk about limits. And we suffer through them for a while. And then from the limit is born the derivative, right? Remember the derivative, the definition of derivative is a limit, h goes to 0, f of x plus h minus f of x all over h. That's the definition of the derivative, but it is a limit, right? It actually comes from this idea. And then we do all this stuff with derivatives, and then L'Hopital comes along and says, hey, guess what? You see these derivatives that we're doing over here? We can actually use these to come back and do limits again, right? So we kind of like used a tool to build a new tool that we're actually using again to make this tool easier. So it's actually very beautiful that L'Hopital was able to discover this sort of thing, all right? So that's why you've had to wait. Sorry. So we will do more L'Hopital. Yeah. It's not always going to be as easy as 0 over 0 and infinity over infinity. It's going to get more complicated, but that'll be next week. Do your homework. I think we're due for a quiz. We've got to have a quiz soon, right?